Hi and welcome again to this series of videos on structural dynamics. We have seen in other videos that damping is an effective way to reduce the vibrations by dissipating the energy present in the structure. Another way is to use vibration isolation, which consists in preventing the vibration to go from an object to the surrounding or from the surroundings to an object. The first kind of vibration isolation we will discuss is direct vibration isolation. Direct vibration isolation consists in preventing an object which is vibrating to propagate these vibrations to the surroundings.
Washing machines and home gym equipment, like treadmills and running machines, as well as bass speakers, are notorious for producing vibrational sound that travels into the floor joists and cavity and irritates the occupants below. We have produced an anti-vibration pad that will help reduce this problem. This 20mm rubber panel is made from recycled car tyres, so not only does it reduce vibration, it is also good for the planet. It decouples the floor from the machine or object and helps absorb the vibration. We suggest you lay them directly on the floor and then add a layer of wooden board on top of the pad to support the legs or feet of the appliance and stop it from digging into the rubber. This can be bought from any large hardware store.
The principle of direct vibration isolation can be understood with this very simple model of a 1 degree of freedom system, where the vibrating object here is represented by M, it is excited by a dynamic force F, and the isolation is represented by a spring and a damper. So the well-known equations of motions of a 1 degree of freedom system are given here. We go to the frequency domain, which leads to the following link between X and F, so the amplitude of displacement and the applied force. Now, if you look at the modulus of the force, we see that it is related to the modulus of the displacement with the following factor. Let's now look at the force that is transmitted to the ground. So the force transmitted to the ground goes through the spring and the damper. And so it is the sum of two forces, the force in the spring, which is Kx, and the force in the damper, which in the frequency domain is I omega bx. We can again relate the modulus of the force transmitted to the modulus of the displacement, so that the ratio of the force transmitted divided by the force applied, the so-called isolation factor, is given by the following expression. Now we can write this isolation factor as a function of the damping factor psi and the natural frequency of the system omega n, and it gives us the following expression. On this graph we have plotted the isolation factor as a function of the normalized frequency, so the frequency divided by the natural frequency of the mass spring system. We see that, of course, when omega over omega n is 1, we have a resonance, so we are actually amplifying the force that is transmitted to the ground. Ft over f is greater than 1. Then after this specific point, which corresponds to square root of 2 times the natural frequency, we see that Ft over f is smaller than 1. So this is what we will refer to as the isolation domain. Now when you want to use an isolator for an object, it is important to know what is the frequency band of the excitation, this f here. And so if you want to reduce the force that is transmitted to the surroundings, you have to make sure that the frequency band of the excitation F is in the isolation domains. So in order to do that, your design variable is the stiffness here. And so if you choose K such that the isolation domain corresponds to the frequency content of the excitation signal, you will have a force transmitted that is decreased. This will result usually in the use of soft spring, so we're going to try to bring the natural frequency of the system here as low as possible. Now, as seen on this graph, if you are putting the natural frequency lower here, it will result in in the isolation domain in a value of Ft over f which is lower. So you would want to put the frequency as low as possible. But of course, the spring here has to be able to withstand the weight of the object, so it is not possible to put a very, very soft spring. There is technical limitations to that. So the effect of damping is also important in vibration isolation. As you see here, if you increase the damping in the isolation domain, you will have less isolation. Now, this means that you would want to have a very low damping, but there are applications in which this domain is important. Think, for example, about an engine or the washing machine we discussed before. So the machine has to start from zero, and as the frequency of excitation is related to the rotational speed, it will have to pass to this point, even if in regime it is rotating here in the isolation domain. So in order to pass this resonance, it is important to add some damping in this case. So the ideal solution would be to have a frequency dependent damping, which is high at low frequencies to avoid this resonance, and low at high frequencies. This is the case of, for example, rubbers and elastomers. So after introducing the main principle of direct vibration isolation, let's have a look at a few applications. So the first example here on the left represents a machine for which springs have been put between the machine and the floor as an isolation. In the second example, you see that two things have been done. The first one is to add a big concrete block to increase the mass and therefore lower the natural frequency, and to add a rubber pad here between the concrete block and the floor. Another example is engines in cars. So they are vibrating and transmitting the vibration to the passenger compartment, and to reduce this effect, engine mounts are typically used. So this is these types of flexible elements with some damping that are used to attach the engine. This is an example in civil engineering where vibration isolation was used for protection of a school building and a hotel complex when a power station was built next to them. So the main ideas developed by the company were that there was an hydroelectric power station that needed to be built, and the school and the hotel should not be disturbed by the vibrations. So what the engineers did is they calculated the optimum natural frequency for the elastic mounting of the power station on the basis of the distributed frequency data from the turbine manufacturer. So you know the frequency band of excitation from the turbines, and from that you can calculate the natural frequency so that you can decrease the force that is transmitted to the surrounding and therefore protect the school and the luxury hotel. Direct vibration isolation is also used for railways. So here we see that we have some ballast, and underneath the ballast there is a sub-ballast mass, so a flexible viscoelastic layer as shown here in the picture. On top of this you have of course the tracks, but the main mass is the mass of the trains passing. Some more complex systems can be used. Here you see that the rails are attached to a concrete slab, which itself is put on rubber bearings. So this is the stiffness and damping our system, and there is an additional mass before the rails and the mass of the train. The other type of vibration isolation we are going to discuss is inverse vibration isolation. So in inverse vibration isolation, the idea is to protect a sensitive equipment from surrounding vibrations, such as here the example of a camera of a drone. So the problem here is that the drone is flying and causing vibrations which are transmitted to the camera, and that can destabilize the image. So here this isolation device is put between the drone and the camera, so that when you are filming, the image is stable. Inverse vibration isolation can also be understood with a simple 1 degree of freedom model represented here, where the perturbation from the surrounding is represented by a ground motion y, and the sensitive equipment is the mass m. So we have seen that in this case the equations of motions are written as this, and so that in the frequency domain we have the following relationship between x and y. Now if we look at the ratio of the amplitudes of the sensitive equipment divided by the motion of the ground, we end up with the following expression. This is called a transmissibility and is actually the same expression as the isolation factor we have seen before. The aim of inverse vibration isolation is to somehow decouple the motion of the building or the sensitive equipment from the ground motion. Now, although the two phenomena, direct and inverse vibration isolation, are different phenomena, you can see that what we want to minimize is either the transmissibility or the isolation factor, and that they are given by the same expression, which means that the curve of x over y is the same as ft over f, although these mechanical quantities are quite different. And so everything we have discussed for direct vibration isolation holds here. We have an amplification domain, an isolation domain, and we can set this point here between amplification and isolation based on the frequency content here of the perturbation, of the ground motion, by adapting the stiffness. Of course, we can also increase the mass to lower the natural frequency. Let's have a look at a few practical examples of inverse vibration isolations of sensitive objects. The example on the left is a microscope which is put on an isolation device to prevent the vibrations from the tables in the surrounding to make the microscope vibrate. This is another example where this is just the isolation table on which any type of precision equipment can be put. This video illustrates the use of an isolation device for a microscope. So as you see, the microscope is targeting this object here, and we are seeing the image. If we magnify the image, as you will see, this image is vibrating when there is no isolation. Now with isolation, the image is now much more stable. Inverse vibration isolation can also be useful to protect pieces of art in museums.
One of the approaches that has been developed here at the Getty Museum is called a base isolation system. And one has to think about it as really a mechanism that decouples the object from the ground while the ground is moving during an earthquake. We have a model of it here, and you can see that it's a three-level mechanism. The bottom level would be attached firmly to the floor. The middle level moves in one of the two lateral directions. The upper level, to which the object is firmly attached, or the exhibition case or the pedestal, moves in the opposite lateral direction. We've got this model attached to a very simplistic earthquake, a very simple form of shake table. So when we turn it on, the table will roughly give a sense of motion the way the earth would move in a real earthquake. Of course, in a real earthquake, it wouldn't be that regular. It would be a lot choppier. It might be considerably stronger, but this gives you an idea of how something might react to an earthquake when it's on the base isolation unit. So we'll put a model of a vase on top, and you'll see that although the vase moves a little bit, it doesn't move anything close to the forces that are being experienced by the table that's moving back and forth and representing the earth. Now, by comparison, if we were to mount a vase on a case that wasn't isolated, I'll just put this vase here and try to catch it as it falls over.
Another application is car suspension. So usually for a comfortable ride, the frequency of these suspensions is set to 1 to 1.5 or up to 2 Hz. Actually, usually for passenger car we are between 0.5 and 1.5. Rally cars have slightly higher, and race cars can go up to 5 Hz. One main issue with car suspension is that if you want to isolate, you have to have a low frequency. But if you have too soft suspension, then you have drivability problems. So more modern suspension systems are called active and are illustrated in the following video.
Massachusetts-based and MIT-born ClearMotion has built some of the most impressive and innovative suspension systems that smooth out the bumpiest of roads, make speed bumps feel non-existent, offer stellar grip and maneuvering, and reduces motion sickness. ClearMotion's suspension systems are so stable that a tray filled with glasses of champagne can seamlessly ride on top of the hood of a car without spilling, and a cake made out of jello barely shakes when the car is in motion. Dubbed the world's first proactive ride system, ClearMotion, which brought out both suspension systems, completely transformed the way your car rides and handles. Comparable to what noise cancelling does for noise, but in this case for motion, it instantaneously alleviates road roughness. What makes ClearMotion unique is that it utilizes and merges state-of-the-art software and hardware to predict and learn the road. This allows for the car to react and adjust before the tires even hit the road. As a result of this instinctual approach, passengers and drivers experience unrivaled comfort, handling, and stability. In other words, ClearMotion replaces a car's shock absorbers with this powerful, fast-acting software and actuators that push and pull each wheel, which delivers an unprecedented car ride experience. ClearMotion equips a car with an active valve that consists of 3 highly sophisticated components working together at sub-millisecond timescales. So when the digital controller detects a potential disturbance, it takes only milliseconds for the active valve motor to counteract it by exacting pressure on the damper. The active valve is one size fits all and is designed to mount on the side of all standard shock absorbers. The active valve's components align with the twin-tube and tri-tube systems that dominate high car volume platforms. Only minor adjustments to a car's body and chassis are needed to activate the smart actuator. A system of 4 active valves creates the digital chassis. It's connected by a central gateway that collects road data and stores it in the cloud to be analyzed and instantaneously retrieved. ClearMotion's Ride OS uses a detailed HD map of the road surface ahead. It also uses advanced control theory algorithms to repeatedly adjust suspension parameters to offer the optimal ride.
And direct vibration isolation can also be used to protect the payload, such as satellite, in space launchers. So at the ignition of the space launcher, you see that a tremendous amount of vibrations is produced in the launcher and likely to be transmitted to the satellite and damaged. So all satellites have to be tested in these configurations. Then when the launcher reaches a higher altitude, there is a separation of the booster, which is done by an explosion. And this also causes high vibrations to the payload. It is therefore very important to use vibration isolation to protect the payload. This is the kind of equipment that is used. So this is soft ride isolators, which are put all along the ring here, where the satellite will be attached, or the payload. So this is represented here. In the fairing of the launcher, you have here a isolation system between the payload and the launcher. Now there are also so-called active vibration isolation in these satellite applications. You see here actuators and sensors which are used to improve still the isolation between the launcher and the payload. Inverse vibration isolation can also be used in civil engineering to protect buildings from earthquakes. So this is the example of two mock-ups of buildings. This one is not isolated at the basis and this one is isolated. We see clearly the difference of transmission of ground motion to this building compared to this building, which will actually lead in this case to the collapse of the building. This video is illustrating in more details what these absorbers, these isolators can be, these base isolators. So the idea is that you insert them between the building and the ground, and they are very flexible elements which are able to protect the buildings in the earthquakes. These types of base isolators then can be put on new structures to make them safer, but they can also be used to retrofit previous buildings without disrupting business. So this is the process illustrated here. This last example is a full-scale test at the University of California, San Diego, where you see that the building is put on a very big shake table, and in this case base isolation is applied and a real earthquake spectrum is applied to the base. They also compared with a fixed base configuration, so in this case there is no base isolator, and you see clearly the improvements brought by the base isolators. Now, as explained in the introduction, it should really be understood that vibration isolation and vibration damping are very different phenomena. So as an example, let's consider a building with 5 stories which is excited by the ground. A simplified model here can be used with the base acceleration and 5 masses representing each of the floors and 5 stiffnesses representing the columns. It is excited by a ground acceleration, which is here again the Santa Cruz earthquake. The question now is, are we going to use isolation or damping to protect this building? So let's first have a look at damping. So the idea here is we start with an initial damping for the whole structure of psi equal 1%, and then we add dampers in the form of B is equal to alpha K. We take here 3 values of alpha, so 0 added damping, 10 minus 3 and 10 minus 2. So what you see here in the transmissibility curve, so this is motion of the 5th floor divided by motion of the 1st floor. It is unitary at 0 frequency. You see clearly 5 resonances of the system which are damped if you add some damping. So if you put 10 minus 2, you have the 4 peaks here which are critically damped, you don't see them anymore, and the first peak is also largely damped. If you want to perform isolation, then we will have to insert a device made of a spring and a damper between the ground acceleration and the building. So in order to design this isolation, we can first consider the building as rigid, and then we end up with this 1 degree of freedom model. And to get the cutoff frequency, we can compute K. So if we want to do isolation to the building, we have to introduce a device between the structure and the ground, which is in the form here of a stiffness and a damper. To design this isolator, we can first consider the building as being a rigid body with a certain mass, and so it reduces to this system where we know that in this case we have the transmissibility given by this curve and the cutoff frequency here corresponding to this point. So if we set this cutoff frequency and we know the mass of the building, we will be able to compute the stiffness of the isolator. For example, if the cutoff frequency is 4 Hz, then the orange curve represents the transmissibility with the isolator. So we see the cutoff frequency at 4 Hz, where transmissibility becomes smaller than 1, but we also see that after that, because this is not a single degree of freedom model, but it has resonances, we have a peak appearing here, and also that because we added the isolator, we have a lower frequency here, lower than 4 Hz in the amplification domain. If we set the frequency lower to 1 Hz, then we see clearly that the orange curve now is much lower than the 3 curves when we added damping, and that the first natural frequency, the amplification domain, is also quite reduced. Now if we put damping in our isolator, so we put a value of size 10% for this damper, we see that the initially gray curve without damping is now increased because adding damping reduces the isolation in the isolation domain. As a conclusion, we can see that isolation and damping are very different mechanisms, that if you are using isolation above the cutoff frequency, if your isolation is well designed, it is generally more efficient but might be more expensive than damping. The mechanisms of damping and isolation are different because damping consists in dissipating the energy in the system, while isolation consists in preventing the vibration from coming to the object. As you see here, doing isolation doesn't prevent having resonances in the system, so that combining the two solutions might also be the ideal option. So whether it is for direct or inverse vibration isolation, it is very important to understand the design principle of such isolators. So what is very important is to know what is the frequency band in which your perturbation acts, and from this frequency band you can define the cutoff frequency of your isolator. So the perturbating frequency should always be in the isolation domain, which often calls for quite low stiffness of your isolator. Of course, apart from the effect of stiffness, it is important to understand the role of damping, which can cause a lower isolation factor at high frequencies.